Okay, so welcome everyone to this afternoon session. Our first speaker will be Shamnon. We also will present their opinion, physics-informed neural network for power grid congestion management. So the stage is yours.
Hello, my dear professor, doctors, and seniors, colleagues. It's an honor to be here presenting my research topic, physics-informed neural network for power grid congestion. Let's get started with the agenda, motivation, data set, methodology, experimental setup, result and discussion, future works. So the most critical problem we want to prevent in power grid in advance is a blackout. A massive blackout swept across Spain and Portugal on last April. All traffic lights went dark. The passenger in the subway got stuck. Not only transportation, but finance, hospitals, communications, stores have been paralyzed. Most tragically, we also lost lives of few people. One was on home ventilator support, and the others like trying to run the old generator and they inhaled the carbon monoxide. Likewise, it can inflict enormous damage and even cost lives. So prevent this blackout in advance is really crucial. So what actually causes a blackout? Whenever congestion or fault happens in a specific region in the grid, to detect the voltage violation, we always need to calculate the AC power flow within a few hundred milliseconds. Otherwise, the protection relay may activate it, potentially leading the cascade trip, which can lead a large-scale blackout. In contemporary grid, we have the renewable energies account for more than 50%, which can occur the voltage violation more frequently. So to curtail this voltage violation and stabilize the grid, it becomes more important to solve this AC power flow within required time frame. So we have this research question: how fast and accurate can we solve the AC power flow using leveraging machine learning instead of using Newton raps, which is a traditional way? So I'm going to walk you through what does it mean that solving AC power flow using this simple example. So we have the graph structure which has 3 nodes. These nodes are called buses. So each buses has types. First, the balance. Second, the consumer. And third, generator. And every buses has basically 2 features. First, power and voltage. And this power and voltage actually a complex number. So in alternating current, it represents as a complex number. So we can separate the real part and imaginary part. In voltage, we separate the magnitude and angle part using an Euler's form. Also, we have line features, which called admittance, is also a complex number separated into G and B. So every bus has these basically 2 features, power and voltage. And here we have 2 unknown variables and 2 known variables. So the solving AC power flow means basically using these nonlinear equations and find the unknown states across all the buses, especially the voltage and angle. So here you can see the nonlinear equation, which is the power, real part and imaginary part. This is actually calculated using the neighbor's voltage and then using the line admittance. So the question now is, how can we solve which algorithm can we use to solve these nonlinear equations? So the traditional way is using Newton-Raphson. So Newton-Raphson is a root-finding algorithm of fx of equals 0. For this, we need to calculate the Jacobian matrix, which consists of the partial derivatives of physics equations with respect to every unknown variables we want to find. And then once we got this Jacobian matrix, we can iteratively update the initial state of unknown variables to reach the solution. But it's actually very accurate in the physics system, but because of this massive computation of Jacobian matrix, it's very heavy computation. So nowadays, we actually leverage neural network. If we have f zeta, we can directly map the unknown initial state of variable to the solution. Under the assumption the neural network f zeta is well trained. This is possible because during the training, the physical structure of this system is already embedded into the parameter theta of neural network during the backpropagation, during the gradient-based learning. So nowadays, we try to replace the traditional Newton-Raphson with this kind of different Newton-Raphson surrogate using neural network. So from like this approximation, this is just simple method, traditional method that just remove the imaginary part of the nonlinear equation. And then the multilayer perceptron is just, as we know, just a normal one, and we can also using graph neural network that can incorporate the information of graph. And then the physics-informed neural network, PNGNN is what I want to explain here. So it actually has a higher speed than Newton-Raphson, but also it has scalability on various speeds. So it can be used any kind of grid size. And even it doesn't need the linear data by Newton-Raphson if we use physics-informed neural network. And at this point, I want to mention one thing, which is operator learning. This is I haven't investigated this well, but if we want to do it very precisely, the physics-informed neural network is not enough because it's somehow, the loss function is somehow gone during the inference. So the operator learning GNN would be the ultimate surrogate of Newton-Raphson for AC power flow calculation. So regardless, I currently focusing on physics-informed neural network for the GNN. So this is just the basic structure that we receive the grid snapshot and using message passing GNN and get the voltage and angle, the unknown state. So the core of graph neural network is the message passing formula. So it has two parts, aggregation and update. And aggregation is just aggregate the message from the nodes, neighbor's node, and using this aggregated message and then update the message of node I. And this aggregation function and update function can be any differentiable equation, like from min max to the complicated neural network. And there are different kinds of message passing has been published in the literature for the graph convolution network, which makes the aggregation and update in a single computation and multilayer perceptron as an aggregator. This is what I have chosen for my network. And graph attention network is also popular, and graph-gated neural network is also widely used. And let's formulate my physics-informed graph neural network for AC power flow. First, I have the aggregation part, and then also updated part. But in between, the physics equation has been plugged in. So basically, we use the line parameter to update the message from the neighbors, and then calculate the features of the node using physical equations and feed them into the update part. So we have, this is basically the node feature, voltage, zeta, and delta P and delta Q. And this is updated also using multi-layer percentage. So here we can iteratively update the voltage, magnitude, and angle, and the message. And the loss function is defined using the gamma decay over the iteration. So to test the performance of graph neural network, I brought a good benchmark data which is recently published by DeepMind. It consists of standard IEEE grid up to the large scale grid, which has 13K buses, but it has a good standard benchmark for machine learning, but it has some limitation as well. This is limited on transmission level, and the topology is fixed. And then this is my main contribution, which is collaborated with electrical energy chair. Overcome the previous data set has only the transmission level. We also introduce the distribution level network for medium voltage and high voltage. And then it actually perturbed the connection, the topology of the graph database, and I checked with the Bradford search. We can reach to the certain node from the starting node. And low voltage network is also available, but currently focused on medium and high voltage. And then this is stored in data frame using Newton-Raphson to get the label, and then also the line admittance and full admittance also stored. And the data is split like this, and then I use two batch strategy. First is same size batching, and then block diagonal batching. So same size batching is just get together same size grid, and block diagonal batching is just diagonally concatenate the grid in any size. And the batching strategy to be explored is like that. So if it is somehow continuous from 1 to 100, the grid side, I want to just pad it up to the n, and then also 64, and then also static constant, like take the maximum size in the batch, and dynamic block diagonal batching, which can leverage mostly the GPU memory. And then this would be my main contribution as well, physics-guided focus sampling. It is just pick the top 4 worst residual buses and build again the mini batches around them. Alright, result and discussion. So actually this is just preliminary result that I got. So I got some good loss curve and this MSE between Newton-Raphson output and then physics-informed neural network output. So here we got a good MSE, but the thing is block diagonal batching is working worse than identical size batching, so this part I want to investigate more. And then I expected the GNS surrogate would be faster than Newton-Raphson like this, and then want to also test on the IEEE grid from the DeepMind dataset, and then also expected to my physics-guided focus batching would be better than different kind of batching strategy. This is I want to explore. And then future direction is incorporate the real data from our collaboration company in host group, and then it actually is stored in the Neo4j graph database like this. And then we also got data from EON, which is a parent company of Leshveake, our collaborator. And this also incorporates a medium voltage grid, and then using OpenStreetMap, it actually introduced the realistic commercial demand patterns, and it has also here medium voltage grid. So I want to conclude my presentation by showing the research roadmap. First, I'm focusing on developing Newton-Raphson surrogate, and then aim to ICASF 2026, and then after that to satisfy the needs of grid operator, which needs very precise result from the Newton-Raphson. I would like to explore a non-operator learning paradigm. And then using this graph neural network I want to apply the reinforcement learning that can find the voltage curtailment level based on the graph neural network. Simultaneously, I want to build the end-to-end graph neural network for optimal power flow by adding additional blocks that can constrain the voltage. And then also fault detection and contingency management, restoration in blackout would be also based on graph neural network. And then eventually I want to contribute about the graph representation learning based on the graph database we built on the Neo4j, storing the real grid from the Leshveake and other companies. Right, this is the reference. Thank you very much. If you have any questions, please ask me. Yep.
Can you go back to slide 15? I think if you... okay. This is where your algorithm is. Quite a few variables.
Yes, yeah.
Exactly. Just let me... Okay. Because this was a bit quick, and it has a lot of variables, and it's not so easy to follow all of them. Mm-hmm. So this is your aggregation from your graph neural network, where you have the NLP here.
Yep.
And then you compute all of those quantities just in a regular way, as in the Newton-Raphson. Is that what you're doing here?
So
these are voltages, powers, and do you ever use the original power network data here, right?
Yeah, exactly.
Okay.
So basically we have like two features, voltage and power in every buses, and we have voltage, and then the current. And these are basically power. So from the voltage, and we using the line admittance of the levers, we can calculate the power. So this is essentially the same of the nonlinear equation I showed before.
Okay, and then you essentially plug this on top so in the classical GNN approach, you would only use this capital M here.
Yep.
And you're saying you're using what you compute from B here as additional features.
Yep, exactly.
But what do you get then? You get essentially new voltages also.
So far, until they see, no update, not the new voltage, but we just plug into the delta P and delta Q.
Okay, and then you...
And then update afterwards the voltage and...
Okay, so you're saying you put additional MLPs on top here, and then you use that for the update here.
Yep.
Just of the algorithm.
Yep.
Okay. Because if you look at your Newton-Raphson and the updates that you're doing there, the Newton-Raphson algorithm you have there is identical to a fully trained resonant.
Fully trained resonant?
Yes. Not sure if you if you notice
I
the
couldn't
equivalence.
understand 100%. So we
Because
connected.
if you look at your Newton-Raphson, you could, if you go to the definition of your Newton-Raphson, no, this is the German. Yeah, here. You see, this is the previous step, and the new. So you have essentially the new one is the old one plus, and then instead of NLP or network, you have the Jacobian here. So this would be identical to a ResNet formulation with as many ResNet steps as you have iterations in the Newton-Raphson.
Yep. But the difference, what I understood so far, as I understood, the difference is Newton-Raphson is directly finding the root.
Yeah.
But the ResNet is updating the parameters.
Yes, that's right. But you can find a ResNet that computes exactly the Newton-Raphson if you use this as a fixed function.
Yeah,
And
exactly.
this is also how you can connect the two methods.
And it's probably the same approach that I introduced with the application.
Yeah, so the problem here is in your Jacobian, this thing is huge.
Yeah, exactly.
And your GNN is much smaller. And this is how you can probably mix the two.
Yeah. So I want to explore about that.
Okay.
And thank you very much.
Okay.
And
sorry, I had to ask a few questions. Stefan.
So to train the network, you train based on the network structure, or how do you actually set it up, and what do you need to evaluate like live, and what do you do before?
So like in physics for neural network, we directly use the physics equations inside the structure. So, and then using this equation we learn, it's kind of unsupervised way. So this is the beauty of physics for neural network. So if we do not incorporate the physics equation, we can just make the loss function with the output of Newton-Raphson. But the physics equation,
Is it change the network afterwards, or is it you need to train the network for a fixed network structure, and then you can only do exactly this network structure?
so yeah, with the network structure is not variated, it is fixed somehow. And then, if I understood correctly, your question is fixed. Yeah.
All right. Thank you very much for the presentation.
Thank you very much.
To set up